Lee. She'll be talking about like zeta functions. So kind of if you've heard of the Riemann zeta function, kind of like that. And she used to teach my Algebra 2 class in that last year. So yeah.
Well, thank you for the invitation. I'm glad to see a lot of familiar faces, including the experts over there. So if you have any questions, you can ask them. Okay, so I hear that there are some freshmen, maybe sophomores, and probably not everyone has taken number theory course, I presume. So we're going to start very easy. Okay, so, well, let me start with the question. How many prime numbers are there? Yes?
Countably infinitely many.
There are countably infinitely many. How do you prove that?
You assume for contradiction that there are finitely many, then you multiply all the prime numbers together, you add one, and then you show that's not divisible by any of the prime numbers. Contradiction.
Exactly. So, well, we have our primes are there, and the answer is infinitely many. And how you prove it? We're going to use the proof by contradiction. We suppose that we have finitely many of them. We multiply all of them together, add one, then that's not divisible by any prime, so we must have another prime, right? So then, yes. But there is another way of showing that there are infinitely many primes, which is using the Euler's method. Does anyone know about the proof by Euler? Yes. So there are people who know about this. And there are people who don't know about this. So let me just say a few words about that. So what we're going to do is we're going to consider this function. Okay. This is going to be, well, this is going to be a function of s. And let's, for a minute, consider that this s is just real number. Okay? Then, well, this is an infinite series. And from calculus 2, we know when this is convergent. And that is when? Yes?
When it's converged is when the s is greater than 1.
Exactly. So this converges where s is greater than 1. Okay, so then we're going to use the fundamental theorem of arithmetic, which is the unique factorization of integers, right? And what we're going to get is this. Because we have prime factorization of n, we can write this as 1 plus 1 half to the power s to 2s, and then times 1 plus 1 over 3 to the power s, 1 over 3 to the power 2s, and on and on and on, times 1 over 5 to the power s, 1 over 5 to the power 2s, and on and on, for each and every prime. Okay. Then, well, this is basically 1 over 1 to the power s plus 1 over 2 to the power s, 1 over 3 to the power s, 1 over 4 to the power s, and on and on and on, right? So we can actually construct each and every number using the prime factorization. So for example, this will come from multiplying each one of the ones in the front. 1 over 2 to the power s comes from this times 1 times 1 times 1 times 1. And 3 comes from this times, and on 1. And then 4 comes from this factor, which is 2 to the power 2s, and 2 squared is obviously 4. So this times this everything 1, that's going to give me 1 to the power 1 over 4 to the power s, and we can find everything like that. So then what do we get? So the general term for this is going to be 1 plus 1 over p to the power s, 1 over p to the power 2s, and on and on and on for every prime p. So I can rewrite this as product over all the primes, 1 plus 1 over p to the power s, 1 over p to the power 2s, on and on and on. Okay. Okay, well, now, this is a series, again. This is a geometric series with a common ratio, 1 over p to the power s, right? So this is a geometric series. And the common ratio, just say r, is 1 over p to the power s. And because we're only considering s to be larger than 1, this is obviously less than 1. So the geometric series becomes, this geometric series becomes the initial term minus 1 minus the common ratio, right? So this is going to be about this series. So this whole thing is going to be product over all the primes, 1 over 1 minus p to the power s. Okay. Okay. Now, let's so this whole series is equal to this. Now, let's take my s, my variable s, tend to 1. So we're going to tend it from the right hand side. So I'm going to tend my s to 1 from the positive side. Then, well, as s approaches to 1, this is going to diverge, right? This is going to be getting bigger and bigger. So the left hand side, yes, and is 1 to infinity, 1 over n to the power s will go to infinity. Okay, well, this is equal to this, right? So that means product over prime, 1 over 1 minus 1 over p to the power s also approaches to infinity. And, well, I'm tending s to 1. So this basically says, let me just write like this. Okay? All right, now, well, this is product, so we can take a reciprocal. If I take a reciprocal of some product, what that does is it takes the reciprocal of each term and then multiply together, right? So this will tell you 1 minus 1 over p is in fact 0. Okay? Now, let's look at that. All right, so now what we're going to do is we're going to take a log to make from product to addition, right? So, and then we simplify a lot of things. Then what happens is we're going to get the summation over all the primes, 1 over p is infinity. That's what we get. What does that mean? This means we're adding like fraction of numbers, right? Small numbers. We add over all the primes, we get infinity. How many primes should we have? We should have infinitely many. So, yes. So this is going to be another proof of the fact that there are infinitely many primes. Okay, then the next question I want to ask is, all right, we know that there are infinitely many primes. Then how often do they come up among all the positive integers? Okay, so the question is how often do they come up? Right? Okay. So, well, one of the obvious answers is, well, the primes is a subset of positive integers. So they will appear less frequent than all the positive integers, right? So one answer is they are less frequent. They are less frequent than the set of all the positive integers. Another obvious answer we can get is I'm going to compare this with this. Right? Okay. Well, this is a p-series with p equal to 2. This is convergent, and we all even know the value, right? Well, we are adding, because we are adding infinitely many stuff here, but it is convergent. What does that mean? They are far less frequent than primes, or even from the natural numbers. Pi squared, sorry. Yes. Right? So, this tells you that they are more frequent than the primes are more frequent than squares. Okay. All right. Then let's try to make it make this value very close to divergent. Okay. So I'm going to compare this with 1 over n log n squared. Okay. Well, this is again on infinite series. We can use the integral test to show that this is convergent. Okay. Well, what does that mean? That means primes appear more frequent than n times log n squared. So primes are more frequent than n log n squared. What does that mean? That means, this means so the primes up to some real number x. So if, for example, if x is 10, there are 2, 3, 5, 7. These are the prime numbers. So this is going to be 4. Right? So this is the number of primes up to x. This is going to be greater than or equal to x by log x squared for a lot of x. Okay. All right. In fact, in when was it? 1796, Gauss observed that pi of x is about the same number as x by log x. If you were in my number theory class yesterday, we talked about this for a week now. Yes?
How did he just brute force it to observe? Or
That's how he did it, right? Yes.
Computer really loves.
Yeah, he did a lot of computations and figured this out, basically.
Wait, like analyzing an engine thing
by hand.
by hand.
Yeah, literally by hand. It was in 1700s.
Before Loveless, right?
So yeah, he actually did a lot of computations. I think if you Google like the images, there's images of his computations. Yes. Okay, so, well, so far, I hope I kind of convinced you that this weird looking function tells you a little bit of how many primes are there, or how many we should expect, or how they are distributed. Okay? So, in fact, this function we've been talking about, 1 over n to the power s, we call this the Riemann Zeta function. And if we allow this s to be complex valued, then it carries a lot more information. Right? Yes. Alright, so let's look at this function. So, well, a lot of properties carry over. So this is convergent, where the real part of s is greater than 1. And then we also have this type of thing, which we call the Euler product. This also is true. 1 over 1 times 1 over the power s. This is also true. Yes. All right. So let's look at some properties of this Riemann Zeta function. Okay. So the first fact is, in this region, if the real part of s is greater than 1, then this is holomorphic. What does holomorphic mean? Does anyone remember? Yes.
Complex differentiable on some open set.
So at each point, we can have the neighborhood where the function is differentiable. Okay, good. And then, so our function is initially only defined over the real part of s greater than 1. But I want to make some sense over the whole complex plane. That is called the analytic continuation. Okay. So when we do the analytic continuation, then what's going to happen is we're going to actually have a pole. With simple pole at s is exactly equal. Okay, and the third important fact is that we have the Euler product. Okay. And we have a functional equation. So the Euler product is this product. And the functional equation is, so we can relate zeta of s with zeta of 1 minus s. Okay. It's not exactly equal, but it's very similar to 1 minus s. Alright, so now we have an analytic continuation. Now we have an Euler product, and for real part of s greater than 1, this is obviously convergent. And also, well, we're multiplying some non-zero values, right? So this Euler product tells us there is no S such that zeta of S is equal to 0, because we are simply multiplying a lot of numbers, non-zero numbers. Okay, so there is no S such that a zeta of S is 0. Okay, and then, so for real part of greater than 1. And then we have a functional equation. So let me draw a picture, right? This is the real part. This is the imaginary number, imaginary part. Then when real part of S is greater than 1, there is no 0. We have complete understanding of this. Now, using the functional equation, what this is going to tell me, because I know everything about this, and this functional equation is very explicit, I'm going to have all the information where real part of S is less than 0. So we know what happens in this region. In fact, there are zeros. So if zeta of S is 0 with the real part of S less than 0, then S has to be negative even integer. So only the zeros will appear on the x-axis. Okay? Alright, so then the only mysterious part is in this part where the real part of S is in between 0 and 1. So this is where all the questions are. Okay? Okay, so alright, so now I'm going to tell you what we believe. It's not proven, but I believe in Riemann hypothesis, so I'm just gonna say we believe it. Riemann hypothesis. This is going to predict where the zeros are in that region, which so if the real part of S is in between 0 and 1, and zeta of S is 0, then the S has to be of the form 1/2 plus IT. Meaning, in the picture, so we don't have any zeros here. We have zeros in the even integers. All the other zeros that makes Riemann zeta equal to 0 has to be on on this half line. Okay. Yes. We call this region critical strip, and where the real part of S is 1/2, which is the midline, we call this critical line. Okay? Alright, so what do we know about these this? How close are we to the Riemann hypothesis? Unfortunately not very close. But let's see some of the things we already know. So, first thing we know is that we don't know about anywhere else, but we do know that on the critical line, there are infinitely many such as that makes Riemann zeta function 0. So, there are infinitely many zeros on the critical line. And, so we know quite a lot of zeros on the critical line. The smallest one is around 14 point something something. The second one is 21, and then 20, I think 5-ish, and on and on and on. And so they crowd more and more as we go up as we increase the t. They tend to crowd closer and closer as we go up the line. And the third thing we know is up to like 13 trillion, the t being 13 trillion, we know that there is no zeros outside of the critical line. T how do I write trillion? 1,000, million, billion, trillion. There is no zero outside. Okay. And this has been shown computational. Yes.
Isn't that where 40% up to where 40% of all the zeros in that region have to be
We know
separate?
at least 40% of the zero is on the line. Yes, but that doesn't really tell you a lot about the zeros off the line. So, yes. All right, questions so far? Yes.
Yeah, I know that the answer might be technical, but is there any reason why they can crowd closer and closer together as you go up the line?
Well, I think it was a computational result. I don't know if was it proven?
Is what proven? Because they do actually get closer and closer.
Yeah, but
Yeah.
but then, do we know why?
Because it grows like d log b, right? D.
So the average distance between them has to be like 1
1
over
over
g.
Yes. Yes.
Actually, do you know why logicians can claim that Riemann hypothesis is independent from ZF?
Independent from what?
ZF, 这没有反的。
I don't know.
Like what kind of magic is going to happen if they are going to show like it's independent? Do you know?
Absolute magic.
I don't know. I don't know the answer. Okay, so now we are going to look at some of the consequences. Well, I'm trying to avoid being technical, so I'm not going to really prove anything. I'm just going to, show you hand wavy of what sort of things should happen. Okay. All right. So the first consequence, if the Riemann hypothesis is true, these are going to happen. So the line of x, this is the, I guess, did I erase it? Yes. So this is about 2 to the power x, p by log p squared, right? This is the line of x. Sorry, it's just log. Right? Yes. I think so. So this is the line of x. So this is about the size of the primes of the x. So let's look at the difference between this line of x and pi of x. Okay. Then I'm going to claim that this is going to grow like square root of x times log x. Okay, so this is going to be about square root of x log x. In fact, I can tell a little more. So let's divide both sides by that. Then it should be about 1, right? And then we know a little bit more. Gamma, which is 1/2 plus I gamma equals to 0 sine gamma log x divided by gamma. So what does it say? Well, let's look at the summation right here. So this is the summation is over the gamma, where this gamma is the imaginary part of the zeros on the half line, right? So this will tell you that the number of primes has a very deep connection with the zeros on the critical line of the Riemann zeta function. And let's see. So this sine function makes the things oscillate, right? And then we have log x, meaning this is oscillating very slowly. And then we're even dividing by gamma. So if gamma is large, well, the top is already very small, right? It's less than 1. So this whole thing is going to be very small. So the zeros that actually matter are the zeros that are in the lower part of the on the line. Yes. So why is this a consequence of a Riemann hypothesis? So without a Riemann hypothesis, so I think pi of x is lie of x plus big O of x exponential log x by log x to power 1/5 3/5 here, 1/5 here. So, well, this consequence says the difference is about square root of x log x, where what we know is that the difference is going to be x times something. So this is much bigger error. So this is the Riemann hypothesis is going to give us much sharper bounds for the number of primes of x. And then the gap between prime. So I want to see how they are distributed, right? So then I want to see how often they come together, right? So let's say piece of k is the k prime, and piece of k prime plus 1 is k plus 1 prime. Okay? I'm going to look at their difference. This, with the Riemann hypothesis, is like pk log pk. In fact, I think like some people conjecture this will be this is going to be over square root of px, but this is even stronger than the Riemann hypothesis. So to show this, Riemann hypothesis is not enough. We need something stronger than that. All right. Another consequence is going to be something called the Lindelof hypothesis. All right, so what does this say? This says that the values on the critical line, well, we know that there will be a lot of zeros on the way. So then if they are not a zero, then how big this can be? That's the question of the Lindelof hypothesis. How big can it be? And the Lindelof suggested that this is going to be very small for any positive epsilon. This is going to be very small. Okay? Why? Why does the Riemann hypothesis say Lindelof hypothesis? That's because, well, we have zeros so very often. Then, and this is a continuous function, it cannot grow too fast. Right? It cannot grow much. So the Riemann hypothesis suggests the Lindelof hypothesis. And people have been finding some non-zero regions within the critical strip, but we're not very close to solve the Riemann hypothesis, unfortunately. All right, now, so then I want to look a little more closely to the size of the function on the critical line. Okay, so that is a study of subconvexity. I heard David didn't like subconvexity problem, but that's okay. Yes. So we're going to talk about the subconvexity. All right. So we have this. So I want to look at how fast or slow this grows as t grows up to infinity. Okay. All right. So in order to do that, I'm going to introduce the Lindelof mu function. right? So what this Lindelof mu function, what this is that so for a fixed sigma, I'm going to let my mu of sigma be the lower bound mu such that okay. All right. So what do we know about this mu function? Well, first of all, because the Riemann zeta function is continuous, this is also continuous. Right? And because this part, everything is convergent. Yes?
So this is not to be confused with the Mobius mu function, right?
This is not the Mobius mu function. This is Lindelof mu function. So, this part, we know that as long as the real part of S is greater than 1, we know that it's convergent, right? So this means this is very small. Like this is small, right? So, so mu of sigma is going to be 0 as long as the real part of S, which is sigma, is greater than 1. Okay. And we have the functional equation relating zeta of S and zeta of 1 minus S. So this will give you the size of mu of 1 minus S, right? 1 minus sigma. So mu of sigma, yes, sigma is 1/2 minus sigma plus mu of 1 minus sigma. Okay. And then what do I know? Well, okay, mu of sigma is 0 if sigma is greater than 1. So if this is greater than 1, that means sigma is less than 0, then this whole thing is going to be 0, right? So that tells me if sigma is less than 0, then this whole term is 0. So mu of sigma is 1/2 minus sigma. Okay, and we know that this is continuous, non-increasing, and convex. So this convexity comes from the Riemann-Lindelof principle, which is basically the maximum modulus principle for larger domain. Okay. Okay. So, yes, let me draw a graph of sigma and value of mu. Well, from 1 and on, I have color chalk. We know that from 1 and on, the value is 0. And if sigma is less than 0, then the mu of sigma is a linear, right? And it starts from 1/2, and then it has slope of -1. So again, the question lies between 0 and 1. Okay, so, and then the convexity will give me that this is the largest domain we can have is connecting these two, right? And how low can we go? Well, because this is convex, I can't go beyond the slope of -1. If I go -1, more than -1, then it's not going to be convex. So the largest, the farthest I can go is like this. And the intersection point is 1/2. Right? Okay, so then my mu in this region is going to be in between this somewhere. Okay, so this tells me mu at 1/2. We're always interested in 1/2 point. So my mu of 1/2 is in between 0 and 1/4. Okay. So this is going to be in between 0 and 1/4. Okay. So then by the definition of the Lindelof mu function, this actually tells me that, oh man, I don't have enough time. Alright, so it tells me that zeta of 1/2 plus IT is bounded by 1 plus t to the power 1/4. Let's be safe. Let's have that one. Okay. Now the question of the convexity is to beat this 1/4. I want to have it as close to 0. Okay. That's what the Lindelof hypothesis is saying. Okay. Well, unfortunately, we're not very close to solving that. So yes. So the question is, eat 1/4. So we have been making some progress. Well, we being a lot of great number theorists, not me. So yes. So the first important result came in 1921 by Hardy and Littlewood, which reduces this to 1/6. So they reduced it to 1/6. They used like Bayes' approximation, like estimating like exponential sums and stuff. And then the best known result so far is it came in 2016 by Jean Bourgain, which says this, he reduced it to 13/84. This is 0.166-ish. This is 0.155. So we've saved about 1/100. Okay? But this is the best we have so far. Okay, so I have 7 minutes. So now I'm trying to talk a little bit about like recent stuff on the subconvexity problem. So in order to do that, I want to introduce this theorem by Eun Hye Lee and Minkowski. What it says is there are by Eun Hye Lee and Minkowski, it says there are finitely many number fields up to with discriminant up to some value n. Alright, so we know there are finite infinitely many, then the next question is, how many, right? Well, the answer is rather disappointing. It's quite random. We don't really know much about it. So then the next question is just like how we saw how primes, how often do they come? Like how often do we expect them to come, right? So then the question we ask is how many on average? Meaning how many do we expect there to be? Well, the answer on this question is quite well known if we only consider the quadratic fields. But if we even go up to the cubic fields, it's not exactly easy to see. Well, there is a very famous theorem by Davenport and Hale-Brock, which came out in 1971, that if I want to count the number of cubic fields with discriminant up to x, some positive number x, so the number of cubic fields with discriminant in between 0 and some value n, then this is going to be 1 over 12 zeta 3 x plus little x. Well, unfortunately, if you do the numerical computation, this doesn't really fit very well with n being like 10 to the power 7 with very large discriminants. This doesn't really work very well. So people have been working on to find like better estimates, meaning we want to find some another major factor that will apply to the number of cubic fields. And that is the theorem by Bhargava, Taniguchi, and Thorne, saying n of x is, and then we have 1/2 divided by 5 gamma 2/3 cubed theta 5 over 3. X to the power 5 over 6. And then big O x to the power 2 thirds from pi plus epsilon. And, well, we're counting the number of cubic fields. What did we say about counting functions? We said the zeta functions are the counting functions, right? So we're going to construct a very special zeta function called Shintani zeta. Okay, so the Shintani zeta function is of the form. We have two different, it comes in a pair of zeta plus and minus of s. Vz mod by SL to Z, x is in this, and discriminant of x is plus or minus, depending on the sign right here, 1 over the size of the stabilizer, x, 1 over the discriminant to the power s. Alright, so what is the summation over? This summation is over V sub z, which I haven't defined. This V sub z is going to be the collection of the binary cubic forms with integer coefficients. So this is going to be x is going to be of the form a u cubed dy u squared v c u v squared plus d v cubed, where a, b, c, d are all integers. And we have the discriminant of x is of this thing is b squared c squared minus 4ac cubed minus 4b cubed d minus 26a squared e squared plus 18abc. Meaning this is very explicit. I'm just telling you this is very explicit. Okay? Alright, and then we're going to normalize by the size of the stabilizer. Let me not worry about this now. Okay? So, then, well, I wanted to count the number of cubic fields. Why am I counting over the binary cubic forms, integral binary cubic forms? That is because of this famous theorem by Delony and Fanny. And then later generalized by Gangrel 7. Correspondence, which relates the the cubic ring with integral binary cubic forms. This correspondence is also very explicit. This is discriminant preserving bijective. So if we can count the integral binary cubic forms, we can count the cubic rings. And what is the cubic ring? Cubic ring is the ring of integers of a cubic field. So we have the connection there. Okay? So as long as we understand this function, then we have an understanding about the number of cubic fields. Okay? Alright, so this function has some erratic properties. Alright, so let's compare this with the Riemann Zeta function. So Riemann Zeta function was has analytic continuation. Well, this is also convergence for real part of s greater than 1. So it had analytic continuation with simple pole at x equals to 1. This one has another pole. So analytic continuation with simple pole at s equals to 1, obviously, and pi equals 6. And then this also has some weird looking functional equation. This is not as pretty as the functional equation of the Riemann Zeta function, but there is at least one of the functional equations. Alright, another nice thing about the Riemann Zeta function was that it was multiplicative, meaning it had Euler product. This weird looking zeta function unfortunately doesn't have an Euler product. And like a lot of zeta functions without Euler product, it unfortunately does not satisfy the Riemann hypothesis. Okay. Alright, now we don't have Riemann hypothesis for that weird looking zeta function. And one of the one of nice consequence of Riemann hypothesis was the Lindelof hypothesis. But we don't have Riemann hypothesis. Do we still think we have Lindelof hypothesis? Well, I believe so. This is still a conjecture. This is a hypothesis. It hasn't been proved, but we believe that the Lindelof hypothesis is still satisfied for this Shintani zeta function. So then we can talk about the subconvexity problem. So we have subconvexity problem. In the setting of Shintani zeta function. Okay, so for the Riemann zeta function, we had mu at most 1/4, right? Now, let's look at the discriminant. This discriminant, everything has degree 4, right? In some order. Everything has degree 4, so this discriminant is homogeneous polynomial of degree 4 in A, B, C, D. So my convexity bound for, or the trivial bound we had, this is one quarter times 4 plus epsilon. This 4 comes from the degree of this discriminant. So what does it say? This is basically 1 plus epsilon. This is going to be the trivial convexity bound. Okay. Now the question is, can we beat this? Can we lower this exponent? That's our question. So I guess as the last thing to say, I'll just state my theorem. So this is with Professor Huff in the 4th floor and me. So we actually did save a little bit. To power 99, 8 over 99 plus epsilon. So we've saved 1 over 99. Well, you know how small we can save. This is how we can save. How